Hello, everyone, and welcome to the second installment of the Universal Gravitation video tutorial series. Continuing from the cliffhanger from the last gravitation video tutorial, we were talking about orbits and how if you had a mass and then another mass and they were orbiting. Let's say that M2 was orbiting in a perfect circle, then we could draw a free body diagram like so. And we talked about how each mass was exerting, or each planet was exerting an equal but opposite force on the other. And we talked about how if M2 is orbiting in a perfect circle, then we can apply Newton's second law, and M2 is doing the accelerating, and it is accelerating centripetally. And so the only force that's acting on M2 is Fg. And we said that AC was V squared over R. And then Fg, the universal gravitation equation, was big G M1 M2 all over R squared. So we take that, plug that in for Fg, and we get G M1 M2 all over R squared equal to M2 times V squared over R. And in your lab, you solve for G, and in your universe, most of you got 9,986.5 or something like that, and then some of you got 10,000. Either of those is acceptable. It just all depends on how you round and whatnot. Okay, but looking at this, we see that the mass of the planet doesn't really matter when it comes to this equation. And if I multiply both sides by R, then that R cancels and that R cancels, leaving me with G, capital G, times M1 over R equals V squared. Now that velocity is the orbital velocity. Okay, that's the magnitude of its speed. And G is the gravitational constant. M1 is the mass of the center object. Center object. There it is. Nope. Object. There it is. And then R is, of course, the distance between our centers. And so if we wanted to, we could square root both sides and solve for velocity. Or we know that the velocity is 2 pi R over T. And so sometimes it's useful to get to solve for the period. And so real quick, I'm just going to solve this for velocity. So I get an equation for the orbital velocity as the square root of capital G times M1 over R, which is a useful equation. But now I'm going to take this and I'm going to plug it in for V. So I still have G M1 R equals, so I'm going to square this whole thing. So I've got 2 pi R over T squared. Okay. So, So 4 pi squared R squared all over T squared. Okay. So now I can solve for the period, and really I can just cross multiply this. So I have T squared G M1 equals 4 pi squared R cubed. Now I can divide both sides by G M1. T squared equals 4 pi squared R cubed over G M1. Square root both sides. And I get T equal to, square root of 4 is 2. Square root of pi is pi. Square root of R cubed over G M1. And that is the equation for the orbital period of a planet, as long as you know the mass of the central object, the gravitational constants for your universe, and then you know the distance between the two. So these are two very useful equations. Now, what you can do is you can compare the periods between two masses, because if you look at both of these equations, do you see how the mass of the orbiting planet or the satellite isn't in there at all? M2 is nowhere to be found in either of those equations. So it doesn't matter how massive the orbiting planet is, so long as you know the mass of the central object. Now again, that holds as long as the central object is very large comparatively. And so in your lab, you had your central object, and then you had an orbiting mass at a distance of 100, and then you had another one at a distance of 200. And you were to compare the periods between the two. Okay, so let's look at, I'll call this M2, and here's M3, and let's call this period T1 and this one T2. Okay, so T1 would be 2 pi square root, R is now 100. So I've got 100 cubed over G M1. Okay. Now, realistically, I could just keep this as, I could just call it R for right now. I'll show you why I'll do that in just a second. T2, if I put it in terms of R, then this is 2R. So T2 is 2 pi times the square root of 2R cubed all over G times M1. So looking at T2, that's 2 pi square root of 2 cubed is 8. 8R cubed times G M1. Okay, now the square root of 8, we can rationalize that as the square root of 4 times 2. So the square root of 2 is, the square root of 4 is 2. So that's 2 root 2, which means that I can simplify this 8 like this. It's square root 2, 2. T1 is this right here. So that's 2 square root 2 times 2 pi square root of R cubed over G times M1. That is T2. This right here is T1. In other words, T2 is 2 square root 2 times larger than T1. Okay? And so what I did is I got T2, the period of it, in terms of T1. You can also do that with the velocity. So let's say that our inner mass here, or the one at 100, is V1, and I'll call this V2. V1 is just the square root of G times M1 over R. V2, square root of G M1 over 2R. So if I get this in terms of like so, it would be 1 over the square root 2 times the square root of G M1 over R. And this is V1. 1 over square root 2 times V1. Now, if you do that operation on your calculadora, and so if I go the square root of 2, that's 1.4, blah, 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 blah. So 1 divided by square root 2 is a smaller number, which means V2 is less than V1. Why is that? If you did the calculation in your lab, in your My Solar System, you should have gotten V1 as like 223 or something like that. And then V2 was 158. Okay, looking at that, and again, that won't hold with, but V1 is moving faster because it's so much closer. Its R value is smaller, which makes this whole equation larger. So it makes sense that V1 is moving faster because it's closer in. Which is why, if I were to show you a diagram like this, and I said, you've got 2 satellites, call this one like that, and I just asked which one is moving faster, it has to be the closer one. Because it's closer in. The mass of the satellites doesn't matter. This satellite could be 3 times the mass as this one. It wouldn't matter because the first satellite is closer. So those are the types of problems that you can expect. For instance, if you, let's say that you have a certain weight on a planet that just has a mass. Let's say you've got a planet, and let's call it planet X, and it has a mass m and a radius r. And then you want to compare your weight on planet Y that has twice the mass, but it has half the radius. Okay, so let's call this mx, rx. So planet Y has a mass that's twice as large, but it's half the radius, which means it's a lot more dense. Okay, so on planet X, my weight is given to me as g m1 m2 all over r squared. That's my equation. And so if I plug in the values that I am, let's say that you have a mass m2. So that'd be g m1, we'll call that the mass of planet X times m2 all over rx squared. On this planet, the force due to gravity is different. So I'll label this one FGX, FGY. Here I've got G, but now the mass of this planet is 2mx times m2 all over the radius is half, so it's 1/2 rx squared. So simplifying that down, FGY, I've still got, I'm going to bring that 2 out. So I've got 2g mx times m2 all over 1/2 squared is 1/4 rx squared. Now dividing by 1/4 is like multiplying by the reciprocal, so this FGY is 8g mx m2 all over rx squared. And hey, does that look familiar? That is that right there. FGY is 8 times FGX. In other words, on planet Y, you would weigh 8 times as much. Because think about how much denser the planet is. That is why you weigh so much more. Specifically, you weigh 8 times as much. So a lot of times you have problems like this where you have to compare 2 different planets, or problems like before where you have to compare 2 satellites, so on and so forth. And there's no calculation. It's just putting the equation in terms of the other. So for instance, simplifying this equation down and knowing that this right here is FG